Good afternoon to one and all. This session will be taken by Professor Indrajit Sarkar from NIT Rourkela on topic Power Flow Control of Triple Active Bridge Converter in DC Microgrid. Dr. Indrajit Sarkar received PhD degree in Electrical Engineering from IIT Bombay in 2018. He has nearly 7 years of industrial experience working in the areas of power electronics converter for renewable energy and HVDC. His area of research interest are EV battery charging system, DC-DC converter, multi-level converter, its control and applications, modular multi-level current source converter, its control and applications, induction heating, induction motor drive for high power applications. He completed his BE degree in electrical engineering and ME degree in power electronics specialization from IIST Sipur. From August 2005 to June 2010, he has served as an assistant system engineer from Energy and Utility Customers Tata Consultancy Service Limited, Kolkata. From 2012 to 2017, he was a full-time research scholar with the Department of Electrical Engineering, IIT Bombay. From 2017 to 2019, he has served as R&D engineer in HVDC grid system with ABB Global Industries Service Limited in India. In July 2019, he joined as an assistant professor in the Department of Electrical Engineering, MNIT Allahabad. Dr. Indrajit Sarkar joined the Department of Electrical Engineering of NIT Rourkela in March 2020, where he is currently serving as an assistant professor. Now I would like to request Professor Indrajit Sarkar to deliver his lecture. Now it is over to you, sir.
Hello. This pointer will work. The screen, it will not work, right? Huh? Acha, changing is possible. Okay, so a very good afternoon to all of you. Today my topic is on this day, I think last topic, last session, last technical session. Okay, so this topic is on triple active bridge DC-DC converter. This is one of the popular DC-DC converter topology where we need isolation. Okay, so one such converter topology which is already in the market and already industries are using is the dual active bridge converter, which is extremely popular and which is extremely useful. This is one step ahead of this. So before understanding of this triple active bridge converter, we need to understand first what dual active bridge converter is. Okay, so this is the presentation outline. So first, let me tell you what is the application. What is the application of triple active bridge converter? Let's say, so this is the triple active bridge converter. This is the triple active. What it is, the detail and all, I will explain you. But before that, let me explain how it is helping. Let's say we have a microgrid, and then we have distributed energy sources, and then we have battery energy storage system. Now you need isolation. When there is a need for isolation, you need a transformer. Okay, transformer. I'm not talking about the size of the transformer or frequency of operation and anything, but let's say we need a transformer. So there is an isolation between every port. Let's say this is one port, two and three, and there is an isolation between these three ports. So we need an isolation transformer. That is first thing. Then we have some converters that I will explain. But here we can see that all these three things are integrated through this single converter, which is called triple active bridge converter. So where it is used, actually generally what we have is when it is microgrid application, there is a need for when there is a grid, there is a need for voltage control. Okay, that can be done using we cannot do using this thing. Okay, it is not possible. So what we need, we need an energy storage system. And nowadays, for better performance, what we are using super capacitors, which are very recent time. But this battery energy system is very much necessary for because there is an intermittent nature of this renewable energy sources. So this is necessary. But at the same time, what it asks for is the isolation. It's isolation. Okay. Because if there is some fault occurs at any other part of the system, it is going to affect this energy system heavily. So what we need is we need it to protect, and that's why we need an isolation. Okay. So this is how we can integrate three things. One is the distributed energy sources, battery energy storage, and this is the microgrid with isolation. Then how this triple active bridge converter looks like? This is the transformer. These are the three windings of the transformer of different turns ratio. And then we have an active bridge here, active bridge here, active bridge here. So three active bridges we have, and then we have three windings. So this makes the TAB converter. Now in this application, what we are showing is it is the integration of this DC microgrid EV charging station with the subgrid, AC subgrid, or it could be AC grid as well. It could be AC grid as well. So this is how it becomes very complex. Definitely, it becomes very complex, but it has several advantages. That is why this research is going on this converter. Now, before we understand this triple active bridge converter, let's understand this dual active bridge converter. Triple means 3, dual means 2. So what we have here is there are two converters, then we have an isolation transformer. There is so two converters, isolation transformer. Now let me talk about what is the characteristics of this isolation transformer. Now what happens here is now there is a requirement for two things. One is size reduction and energy efficiency. Okay. For size reduction, the very first thing that we need is the high frequency operation of this transformer. Why high frequency operation of this transformer? Now let's say so transformer voltage is directly proportional to frequency and flux. Now let's say we have a power frequency transformer where frequency is 50 hertz. This frequency is 50 hertz. So same for same voltage, this flux, you will get some flux. Now when the frequency you increase this frequency now to let's say 25 kilohertz. If you increase it to 25 kilohertz for same voltage, the requirement of this flux reduces like anything. So this flux reduces significantly. When flux reduces significantly, the size of the core of this transformer reduces significantly, because this reluctance depends on the area, cross-sectional area and length of the core. Okay, reluctance of the transformer. So when this flux is reducing, the size of the transformer reduces. That is why the aim is to operate this transformer at very, very high frequency. Okay, so very, very high means there is definitely there is a limit. There is a limit by switching operation, switching losses and other factors also. Now what we do is we have operated, we means the researchers are operating this as at 100 kilohertz as well. Okay, how it is possible, that we'll explain. Okay, but currently what our research is going on, it's something around 20 to 25 kilohertz, and we are using isolation transformer of that range. We have TAB, triple active bridge transformer, that three winding transformer we have, we have at this frequency range, and also dual active bridge converter also at this frequency range. Now thing is, frequency we have increased definitely. So at what cost we have to pay? When we are increasing frequency, increasing operating frequency, this losses in these devices increases like anything. Losses in the devices increases. Okay, but losses are increasing. There will be a shift of frequency. Let's say initially it was, let's say, 98%. Now frequency losses, because of losses, let's say it has come down to 97%. Okay, now if it is 1 kilowatt, uh, if it is 1 kilowatt, the system power level is 1 kilowatt, 1% efficiency improvement is nothing. Okay, if you increase by 1%, there is no harm, but there is harm from other point of view. What is that? When you reduces losses, when you can reduce the loss, when you can reduce the loss, the device loss has reduced. When device loss reduced, the requirement for heat sink reduces. Okay, that is the main point. This devices comes with heat sink. When this loss you can reduce, if you reduce the loss, the heat sink size reduces. If heat sink size reduces, your converter becomes more compact. That is the requirement. Your size of the converter is also important. It is not like 1% efficiency improvement will give you very high energy consumption or something like that. But definitely the size of the converter will reduce because your heatsink size will reduce. That is the main thing. Now what we do is, when we operate at 100 kilohertz, when we operate at 100 kilohertz, at this frequency, the switching losses are further increased. If switching losses further increase, this heat sink size will further increase. So in order to reduce the switching losses at this frequency, what we do is we do ZVS operation, zero voltage switching operation, zero voltage switching operation. This is possible. ZVS is possible. So one major reason for using this dual active bridge converter is this one. This is the main reason why we are using this dual active bridge converter, where we can operate at very high frequency. Their sizes of the components reduces. Also, we have flexibility for ZVS operation, zero voltage switching operation, and we can achieve very compact size of the converter. That is the much requirement. That is the key requirement for a converter. Okay. Now, this is the design aspects. That's fine. Now, how this DAB converter operates? It's a very simple actually. This DAV converter, we are interested on these 2 points. We are interested upon these 2 points and these 2 points. Now, equivalent of this thing is this. One AC source, another AC source, and there is a leakage inductor. If leakage inductor is not sufficient, yes. Acha. Acha. How to use it? Then this is, I think, PDF or PPT. This is PDF, I think. PDF. PPT is also there. Okay, fine. How to erase it? Eraser. Okay, fine. Take it. Thank you. So what we are interested on, we are interested on these 2 potential and these 2 potential. Okay, these 2 potential. Now this equivalent circuit is presented like this. Okay, presented like this. So there is a primary voltage. This is the primary voltage. There is a secondary voltage. This is the secondary voltage, and the equivalent of this transformer is represented like this, neglecting the shunt branch. And this is the leakage inductance of the transformer. And if needed, we add more inductance to it, because designing of this transformer for required leakage inductance is little bit critical. So what we do is we design a transformer. If that leakage inductance is not sufficient, leakage inductance play a very crucial role in power transfer. So if that is not sufficient, we add external inductance as well. Okay. Now this is very simple. This is same way it works, where let's say you have an inverter. You have an inverter, then you have, and then you have grid. So there is an inverter. So let's say solar inverter you have. So it is pumping power to this grid. This grid is infinite bus. Why it is infinite? Because it's from 2013. What we have is, we have one nation, one grid. So grid is very, very rigid. Okay, rigid means its frequency and voltage, frequency and its voltage is constant. Voltage, you cannot say voltage constant, but that depends upon the local impedance and other things, and also the loading thing. But this variations will not be much if it is if you consider this is a rigid grid. and frequency will not vary much, because it's like an ocean of water. If you take one glass of water, one bucket of water, or you put one bucket of water, it is not going to affect its frequency and voltage. Okay, so here also same thing. Here this inverter, this is represented by this inverter, and this is represented by this grid. So there is a power exchange between these two. How it happens? When we put a phase difference between these two voltages, phase difference, let's say one voltage is this VP, and if we put a phase difference between them, phase difference, then there is a power transfer, because when there is a phase difference, there is a current flowing through this inductor, and there is a power flow from one source to other source. This is the simplest way by which we transfer power in dual active bridge converter. So how it is done? So this is called SPS, single phase shift control. This same thing we employ for triple active bridge converter also. So this is the VP, primary voltage. This is the secondary voltage, and this is the inductor current. What we have done here is, you see here, there is a phase shift. So this voltage is something like this, and this voltage is something like this. So there is a phase difference. There is a phase difference between these two, which is called delta or phi. Same thing, same what we do in this case also. Here also we do the same thing we are employing here. So there is a power transfer when there is a phase shift between these two. Okay, then there are other methods. I am not going to explain the dual active bridge converter. I am going to explain triple active bridge converter. Since these are also necessary, just let me explain this. Here only there will be a square wave. We are generating square wave because it's a square wave inverter. It's a square wave inverter. It's generating a square wave like this. And here also this voltage is constant. This voltage is constant. This is an assumption which is not possible as well. Okay, assumption that these two voltage DC voltages are constant, and we are generating square waves of constant peak. And this difference, when there is a phase difference, the difference is appearing across this inductor, and there is a power transfer between these two. We control this phase shift, and we control the power flow. Now there is a problem. There is a problem. Okay, this is a little bit complex. Looks complex phasor diagram, but if I explain, you will understand. Now what happens? This is one phasor. This is another phasor. This is primary phasor VP, let's say, and this is the secondary one, V secondary, two voltage phases. Now I have mentioned of same length, because this is the red dotted line and they are of same length. Only there is a phase difference between these two, and there will be a power transfer. Now thing is, there is a term called K. K means what? There is a turns ratio. Okay, there is a when this transformers are there, there is a turns ratio. So when we refer this voltage on the primary side, this voltage and this voltage will be same. But there is a term called K, which defines the voltage gain. That depends on this voltage. How much is this voltage? If this voltage varies, that K varies. If that K varies, then this phasor tip will vary. This phasor tip will vary. So when these two phasors are of same length, the phasor diagram is this. When K is different, then its phasor will be somewhere here. Phasor will be somewhere here. Because of this difference in phasor lengths, it gives rise to a circulating current. What is that circulating current? It is supplying a power. This voltage is not capable to take the entire power. So what it does is, let's say it is supplying 100 watt, let's say very crudely, it is only taking 80 watt, and the rest 20 watt again returning. So what it is happening, it require 80 watt, but we are supplying 100 watt. So extra 20 watt is circulating in this converter. Okay, that will give rise to extra power loss in the converter. This is the limitation of this SPS, single phase shift control. It's a problem. That's why it is, though it is very, very simple, we use extended phase shift, EPS. Okay, extended phase shift. Similar thing we'll use there in triple active bridge converter. That's why let me explain this. In EPS, what happens is the secondary voltage remains square wave, but primary voltage is a quasi square wave. quasi square wave. Okay, the phase difference between these two is called external phase shift, and this phase shift is called internal phase shift. Okay, there are two phase shift. Here it is external phase shift. This phase shift is external phase shift. Here the phase difference between these two voltages, primary and secondary, is called external phase shift, and this phase shift is called internal phase shift. By internal phase shift, we can control the length of this. We can control the length of this primary voltage. Length of this primary voltage. You see, initially it was here. With change in K, we can adjust this length of this primary voltage, and we can control the circulating power. So that is why this EPS modulation is very, very popular, and it is it thinks to be one of the best modulation technique for dual active bridge converter. Same thing will be extended for triple active bridge converter. Now I'm moving to triple active bridge converter. So first I will explain about few topology, a few topology of triple active bridge converter. This is the conventional triple active bridge converter. So all these active bridges, full bridges. So when it comes to full bridge, why not to use half bridge? So these are the half bridges. So same configuration, you can move, you can use full bridge or half bridge, but there are limitations. There are advantages, disadvantages as well, because here number of switches are more, here number of switches are less, but there are other operating advantages as well. Okay. Then what we have, this is one of the literature proposed this. This is called DTTAB, DT8TAB. So there are two transformers, dual transformer. Here the only this is here you can see it is actually this is showing, this is representing that it is only one transformer. So one transformer. So only one core, and then you have three windings. One core, three windings. In this case, you have two transformers, two different transformers. Okay, two different transformers but integrated with the same secondary side, same side. So two ports are there, isolations are there, and there is connected to the same port. There are advantages on this also, and this is a three-phase version of triple active bridge converter. Three-phase version is for high power application, though the research in this area is less, because even you will understand, even this conventional topology itself operation is a little bit complex. Okay. Okay. Now from here I try to explain the operation of triple active bridge converter. What we have here is we have three ports: port 1, port 2, and port 3, and three voltages: VDC1, VDC2, VDC3, and there are three windings. There are three windings, and their turns ratio, the number of turns are given N1, N2, and N3, and these are their leakage inductances. These are very important. The leakage inductances are very important. Okay, and then we have edge bridges, three edge bridges. Here what we have is our aim is to generate square wave across these two terminals. Square wave across these two terminals. Now let me tell you one thing. Why I'm representing this as a DC source? As a DC source, what happens if you, instead of this DC source, if we connect a resistor here, let's say a resistor here, okay, then what happens? The square wave that we are saying that it will generate a square wave. To generate a square wave, it's kind of inverter. You need a DC source. DC source will generate a square wave. Then only a square wave will be generated here. When there is a resistance, that is not possible. Control strategy will differ in that case. In that case, control strategy becomes the voltage control mode. Here it is current control mode when it is VDC, but when it is resistance, then control strategy becomes its voltage control mode. Okay, so these two are different. Now, as I told you, these are the external phase shifts. Okay, now you'll understand. Now the phase difference, there is a square wave for this, there is a square wave for this. The difference between these two square wave is, this is the phase difference. Similarly, these two. Now you see the problem is there is a phase shift between these two as well. This is 512, this is 513. So phase difference between these two will be either 513. So it is like this mod. Now the problem here is, you when it is DAB, let's say this is not there. There is a phase difference. Power is transferred from this side to this side. Fine. When this is not there, you put phase difference of 513. There is a power transfer between these two. But when there is a presence of these two as well, when simultaneously you have these two, power transfer is happening between this and this is fine. But there is a phase difference between this and this. So there will be a power transfer between these two. Okay. You are controlling, try to control power transfer with these two and these two. But inherently, there is a power coupling between these two. Coupling between these two. So solution is what? Let's say make 513 equals to 512. Then fine, there is a no phase difference. So there is a no exchange of power between these two, only exchange of power between these two. But it is, let's say your battery is charging. And here it is a DC microgrid. Its power level is different, its power level, power requirement is different here, power requirement is different here. When such scenario appears, this cannot be the case. So the operation of TAB becomes difficult. Operation of the TAB becomes difficult. Okay. And then I told you about the internal phase shifts. These are the three internal phase shifts. Okay, between the inner switches, because you have to generate a quasi square wave. So here we have five variables. The external phase shift, these two, and internal phase shift 1, 2, and 3. So 5 variables. That's why equivalent to EPS, extended phase shift, in TAB we say penta phase shift. Penta, because there's a 5 variables. Okay. Now, what are the things? So as I explained, this one and this one I explained. Now, TAB converter offers bidirectional power flow. This is very important actually. Let's say now there is a concept called there is a concept called uh, vehicle to grid power transfer. Okay, vehicle to grid power transfer. So what it does is it's called vehicle to building, vehicle to grid, and vehicle to home. Okay. Now let's say you have a vehicle here. Okay, vehicle. So let's say this is a charging station, and this is the energy BESS, battery energy storage system. And here let's say you have microgrid. Okay. When there is a contingency, it might happen if owner allows, it might happen that you are taking the vehicles are parked and charging. It might happen that you have to transfer power from those vehicles to this system, let's say to the microgrid in case of contingency, let's say. So you have to, let's say this microgrid is one application of microgrid. It's, let's say, a shopping mall. Okay. In shopping mall, owners are having cars. Those are parked at this charging station, and when there is a problem in this microgrid, if it is utmost necessary that we need to supply power, this car you can take power from this car. So if that happens, so it, as it says, that is bidirectional. So every possibility of power transfer is possible, is possible in this scenario. So here to here, here to here, here to there, every possibility is there. Only thing is you have to take care of the phase difference, internal and external phase difference. That is the thing. Okay. As I was telling you, there are different possibilities of power transfer, but all the possibilities are there. Okay, power transfer between all the three ports are possible. So actually, this naming, the work we have done here, we have named like this, but this power is actually P1, and this is P2 and P3. Okay, so here it is supplying power, and these two are consuming power. Okay, so all the possibilities are there, all the possible combinations are there. Power transfer, this is the equivalent circuit. This is called delta equivalent circuit. So same thing, based on phase difference, how the power is flowing. Okay. Now, as I told you, single phase shift control I explained for DAB. Here it is, I'm explaining this for TAB converter. So what we have here is, these are the switching waveform. What we have here is This is VAC1, VAC2, and VAC3. Three square waves we are generating at the transformer terminals. We are generating this. So this VAC1, VAC2, and VAC3. We have considered very simple thing where we are assuming that K is 1. K is 1. If K deviates, it becomes further a little bit complex, but we have assumed K equals to 1. So all the heights are same because these are referred. It should be like this, referred quantities. So you can see there is a phase difference between this waveform and this waveform is given as phi 1 2, and between this and this is phi 1 3. So there will be a power transfer between 1 and 2, 1 and 3. There will be power transfer. But you can see here, it will act as a DAB, these two. There is a phase difference between these two. There will be a power transfer between these two also. So we need to optimize it so that we'll see. That we'll see. So I was explaining like in this here, we are generating VAC1, AC2, and AC3. Those waveforms we have shown, and the inductors are there. Leakage inductance of the transformers are there, and those are the voltage across the inductors. Voltage across the inductors. These are the voltage across the inductors and the current through the inductor. Current through the inductor. So this is how generally this is typical waveforms of inductor current and voltage in case of DAB, in case of TAB as well. Okay. So this is the simulation result you can see here. So actually here it is shown that huge phase difference is represented here, but actually a small amount of phase difference can give rise to very high value of power transfer. Okay. So here we have shown that this phase difference is little bit, but power transfer is happening. Phase differences are shown. So these are the three voltages, and this is the inductor current. Now here you have all the inductor voltages and inductor currents are represented in the same waveform. So three ports are there. So three port inductor currents and inductor voltages for this phase difference, 10 degree, and this is 15 degree. This is important. So this is phi 1 to 10 degree, phi 1 3 15 degree. Okay. These are the powers. This is the P1, this is P1, P2, and P3. So here you can see the power generally looks like this. So there will be an average value. There will be an average value of this power, which is 1196 P1 average. 1196. This is the power transfer by the primary port. Now here you can see here it is this power is 7 minus 739, and here it is minus 441.6. So there is a power there. There is a power circle. There is a these are consuming power. These two ports are consuming power, and this is the source that is supplying power. If you add up these two, it is not equal to whatever power it is supplying. Rest of the power is circulated. Rest of the power is circulated. So we need to know the operating range or region where we can operate so that this circulating power becomes minimum. Circulating, we supply the amount of power which is necessary, not all the powers that we are going to supply. means we are not supplying any extra power. These are the for here you can see here as I was explaining grid to vehicle mode, vehicle to grid mode. Here you see that 513 is made minus 15 degree. Okay, acha, one thing. If let's say one voltage is this, another voltage is lagging. So let's say V primary and this V secondary. Then power will be transferred from here to here. If it is V primary is this and V secondary is this, then power will be transferred from here to here. So it is always which is lagging there we transfer the power. Which voltage is lagging, voltage phasor is lagging, there power is transferred. So here you can see if 513 is given minus, so in that case you see here power has become positive. In previous case you see only just this difference. Here 10 degree and it is plus 15 degree. And so the power was average power was minus this much. But in second case only this is minus 15 degree, but average power becomes positive. It is plus 584. So now 548.8 watt. So now this port 3, this is P3. So port 3 start supplying power to the system. Now this power has reduced. This power has reduced. Now question might arise that here you see this power previously it was minus 441, just only one phase difference. You made change in this phase, but you see here this power has changed. This power has changed to 700 minus 700 watt. This is called coupling effect. You are changing one port power, the other port power is also changing. This is not necessary. This is not acceptable. Let's say a battery is charging at the same time the other port vehicles are charged. Okay, battery energy storage system is charged at certain current level. Let's say 150 ampere current level. Okay, and vehicle is also charged at that time. Now when you remove the vehicle, the charging power of that battery energy storage system disturbed. Disturb means it is not transient, permanently it is disturbed. Let's say 150 ampere to it has become 160 ampere. This is not acceptable. Okay, this is called coupling effect. So this how we can remove this, that I will explain. Okay, so here we can see when there is a change in phase difference, there is a power change in power and also sign of power. This is power flow. There are equations as I told you. These are the power and these are the internal power which is circulated in the sense between the two ports the power transfer. So this is how with 513 512 this power is varying. These powers are varying. Okay, P1 P2 and P3 how they are varying, it is explained in the, because these equations are there. If you fix these things, then you can generally you can plot this. Okay, since there are two variables and there is power, so it is 3D figure. Okay, so as I was telling you, in order to minimize the circulating power, what we need to restrict our 513 and 512 so that the power becomes for any value of 51213 your power is not going to, the circulating power is not going to minimize. There is this sets of equations you need to solve. How to get these sets of equations? This I will come. But you see here, the power 1, power 2, and power 3. These are plotted on same. This is the region where, this is the region. This is the region for which. So this is the region for which it depends. This region, how it will be. This region depends on what power references we are choosing. What power references we are choosing. You see here that the port powers P1, P2, P3 we have taken as K1, K2, K3, and those powers are plus minus. Those powers are plus minus. Now in this equation, these are the port powers. These are the port powers. These are the port power equations. Now if you do Taylor series approximation of these terms, if you do Taylor series approximation of these terms for all the three powers, then you will get these equations, and these will be governed by the reference power. reference power, whether it is positive, negative. So Taylor series approximation, you will get one equation, another equation, another equation. So three powers, P1, P2, and P3. But this constant will come from what reference power that we are going to choose. Okay, reference power. It could be positive, it could be negative. So if you solve this, that will give you the best value of 512 and 513, by which you can minimize the circulating power. For any value of 51213, circulating power will not be minimized. Okay, that these are the things that you need to keep in mind when system becomes very easy. But when you going to operate these things, you will understand that you need to keep these things in mind. These are very simplified. Okay, 1 k equals to 1. Okay, if k not equals to 1, things become worse. Okay, when k is not 1, what voltage we have assumed here, right? You see here, in this term, we have used V1 DC, V prime 2 DC. Here we assume that V prime 2 DC, V prime 2 DC is prime 2 DC is coming from V2 DC. Okay, what is that? V2 DC. V2 DC is this one. V3 DC is this one. K is 1 when these are whatever value. Let's say you have set this value as 75 volt. If it is always 75 volt, K is 1, that's absolutely fine. No problem at all. But it happens that this voltage, let's say if it is a BESS, then its voltage will rise. Its SOC level, when it is charging, its SOC level is changing. Its voltage level will change. So this V2 DC will not remain at 75 volt. It will vary from, let's say, 70 to, let's say, 80 volt. So in that case, your K will not be 1, and you cannot, it becomes very difficult for us to minimize the circulating power. You keep on adjusting these equations, keep on adjusting these equations to find out best value of 512 and 13. That's why that's why this DAB converter, it becomes very difficult for battery charging application when it is in voltage control mode. Current control mode becomes easier, but voltage control mode, when voltages keep on varying, then K keeps on varying and becomes difficult. Okay, here also TAV converter with different when TAV converter, I have shown you this application, it becomes very, when this voltages are maintained, these voltages are maintained, okay, at desired value, then operation of this converter becomes very simple. Very simple in the sense, with decoupled control it becomes very easier. But when these bus voltages are varying, then it becomes a little bit tricky to operate this converter. Okay, this is the star equivalent circuit of TAB converter. So port 1, port 2, and port 3, these are the leakage inductors, three leakage inductors, and it can be represented as delta as well, because there is an advantage, because plotting, it's we have plotted it. Okay, we have plotted it. I have not presented here, because very recently we have come up with the phasor diagram. This phasor diagram and this phasor diagrams are completely different. Actually, it depends on the, here it is the summation of currents, here it is summation of the voltage. So it becomes a little bit different when you represent it as a star or delta, becomes difficult. But these are separately needed in order to understand the voltage control and the power control. Separately we need to understand in order to understand its power and voltage control. Now this is the TAV phasor circuit for two port in TAV converter that I already shown you there. So this is one voltage, this is another voltage. The phase difference is nothing but the inductor drop. This is the inductor drop, and the current is perpendicular to this inductor drop. That's a very simple phasor diagram. But when it becomes three phase, three a TAV converter, then it becomes a little bit tricky. Okay. Now one of the important topic in TAV converter. Okay, DAB converter I explained you. So in first, it is represented the um, circulating the back power flow. Back power flow means you are supplying some power. The source is not able to consume the entire power, rest of the power is coming back. Okay, it is like you are selling, you are supplying some goods to the market, and the consumers not able to consume the all the goods that is available, rest of the good is coming back. Like a fund is coming, let's say 100 rupees is coming, you spend 80 rupees, 20 rupees is going back. Like that it happens, right? So here also it's like some amount of power it is supplying, whatever require more than that we are supplying, but you are consuming only a part of that power. Okay, so rest of the power is coming back. So the extra power has no role other than increasing the losses in the system. So aim is to reduce that extra circulating power. Now when it is SPS, when it is SPS, single phase shift control. So what happens is, this is V1 DC, V2 DC. There is a phase shift. There is no inner phase shift. That is why both the waves, both the AC voltages are square wave, not quasi square wave. If this is the case, this is the inductor voltage, inductor current, and this is the input current. This is the input current, means the input DC current. So input DC current has a negative portion. Input DC voltage is always constant, but it is having a DC, a negative portion. So because of this negative portion, there will be a negative power. That means some amount of power is flowing back. Here I need to explain you one important thing. There is a difference between reactive power and backflow power. Reactive power. Okay. What is the difference between reactive power and backflow power? Now see, there is a voltage phasor here. There is a voltage phasor here. Okay. So let's say there is no phase difference between these two phasors. This phasor, both the phasors VP and VS, both are not, both are of same length, and there is no phase difference between them. No phase difference. So there will not be, this current will be zero. This current will be zero. Okay, fine. So if this current is zero, this current is zero, then the reactive power requirement of this inductor is zero, because that is IL square omega L. This is the reactive power consumption by this inductor. Now let's say, as I was telling you, if K value changes, if K value reduces, K is less than 1, K is supposed to be 1, but let's say K is less than 1, then what will happen? One phasor is this VP, but since K has reduced, VAS has become this. You try to understand this. VS has become this. Okay. Because of this difference, there will be a current. There will be a current. There is 90-degree. This drop is IL into omega J omega L. There is a drop. That means because of this current, there will be, this is the reactive power consumed by this inductor. Okay. Now you see here, there is no phase difference. There is no phase difference. So power transfer from this side to this side is zero. From here to here, there is no power transfer. But still there is a requirement for reactive power, because these phasors are not same. So this reactive power is not nothing but it's backflow power. Okay, even if there is no power transfer, because of the difference between these two phases, there is a power which is circulating, which is not consumed by this Vs. There is a power which is circulating, that is, in terms, this is, you can term it as reactive power or you can term it as backflow power. Because why we are terming it as backflow power because no power is transferred forward. Whatever power is transferred, all the power is coming back. This is called backflow power. Now let's say what is the requirement for this reactive power? What is the requirement for reactive power? When you have a reactive element in the circuit, then you have VPs like this, and then let's say you want to make VS like this. If you don't supply this amount of reactive power, if you don't supply this amount of reactive power, your circuit will not operate. Your circuit will not operate. So you need to supply this amount of reactive power, then only your circuit will operate. Okay, your circuit will operate. But thing is, this reactive power we want to minimize. This reactive power comprises of reactive power plus backflow power. Why I'm saying like this? Because this reactive power will be minimized when this is at 90°. So this has to be, this Vs length has to be here. Okay. So this length has to be minimum, this length. Then only reactive power will be minimum. In that case, this backflow power will be 0. Okay. So reactive power and backflow power, there is a difference between these two. Reactive power is absolutely necessary. Without supplying reactive power, any AC circuit, if you don't supply the required amount of reactive power, the AC circuit will not work. Okay, let's say a transformer is there. Transformer is there. If you don't supply the magnetizing current, your transformer will not work. If it is an induction machine, if you don't supply the required amount of, let's say 30% of magnetization current, your machine will not operate at all. So that amount of reactive power you have to supply, otherwise it will not operate. Okay, but definitely the amount of reactive power which is required can be optimized. When it is optimized, then backflow power will be 0 and reactive power only, the circuit will consume reactive power. So this only can be done by this method, as I explained, that if you solve these equations, this is the zone on which if you operate, then your reactive power will be minimum and the backflow power will be less. So this is the backflow power. So this is backflow power that we are having. Now when we use the backflow power plot, now there is a phase shift. Initially it was SPS, single phase shift control. Here it is PPS, penta phase shift control. As I told you, there are 5 phase shifts. One is the these two, and another is delta 2, delta 3, another should be delta 1. It's not represented here. So there will be 5 phase shifts. Now you see here, acha, here it is delta 1. So this is voltage V1 AC. V1 AC, V2 AC, and this is V3 AC. Now you see none of them are square waves. None of them are square wave. All are quasi square wave. Quasi square wave. What is the advantage of making this quasi square wave? We can see when we have a square wave, then this is its fundamental voltage. Let's say it is V1. So it is the V1 phasor length is this V1. Okay. But if it is, let's say, quasi square wave, if this voltage of same peak, but your voltage waveform is quasi square wave, then fundamental voltage peak will reduce. So in that case, let's say this is V1 prime. So this length will reduce. So by practicing this inner phase shift, so this was the square wave. This is quasi square with a with an inner phase shift of delta. If you increase inner phase shift, the the width of this square wave is keep reducing, and this value will keep reducing. This value will keep reducing. So you can control over the length of the phasor. You can control over the voltage magnitude. Voltage magnitude. That is why inner phase shift is introduced in each of these waveforms. Inner phase shift is introduced. So V1 AC, V2 AC, V3 AC. In each of these waveforms, the inner phase shift is introduced so that the length of the fundamental component can be length of the fundamental can be controlled. Okay, by doing this, what we can do is we can adjust the current phasor. How it can be done? I think phasor diagram. So initially, when delta is zero, when delta was zero, then these two are of same length. When you introduce delta, when you introduce some delta, then what will happen? Let's say this phasor will reduce to here. This phasor will reduce to here. Then drop will be something like this. Drop will be something like this. Automatically, the current phasor will come somewhere here. Current phasor will come here. Initially, current phasor was here. Now current phasor is here. Okay, IL. So automatically we are controlling the current phasor, its length as well as its phase angle. So initially current phasor was somewhere here. Current phasor was somewhere here. Okay. Now as you introduce delta, this length has reduced. This U1 length has reduced. Because of this, this drop has changed. Inductor drop has changed. So current phasor length and its phase angle also change. This is how we control. This is how we control the current flow and hence the power flow. So in penta phase shift, as I told you, there are 5 phase shifts, 2 external phase shifts, and there will be 3 internal phase shifts. So delta 1, delta 2 for all the 3 square waves, and this is phi 12 and phi 13. Okay. Now, what is the difference between SPS and PPS? In if it is a DAB, it is EPS, extended phase shift. Since it is TAB, we have 5 phase shift. That is why PPS, penta phase shift. Okay. So loss of switching, soft switching. Explaining soft switching is a little bit, it will take some time because introduction of soft switching itself, understanding of how the inductor and the parasitic capacitance of the MOSFET is going to play, that is important to understand. Okay, here high circulating currents, as we cannot control over the length of the, because there is in SPS, EPS, SPS is the special case of EPS where delta equals to 0. So we cannot control the current, we cannot control the voltage phasor length, and that is why circulating current we cannot control. Significant of back power flow, definitely. Increased control flexibility, definitely, with complexity as well. Minimized switching losses, as we are reducing the back power flow. That is why we can reduce these switching losses. Actually, not switching, it should be conduction losses. Back power flow minimized, system efficiency definitely increased. RMS value we can control. That is why we are saying ZVS is ZVS range is increased. Just only one line I can say about ZVS at this point, because in ZVS it is very necessary. It is very important to control the current phasor in order to make it leading, in order to have the ZVS operation to be successful. So since by controlling the, as I explained here, that by controlling the length of this phasor, we can control the current phasor. We can place the current phasor at anywhere. So we can control the current phasor phase angle. We can make it leading, we can make it lagging, and that is why the ZVS operation range we can control. Now you can see the difference. This is SPS control, SPS, single phase shift control. So this is significant of back power flow is there. Okay, because this is negative. This is current, I think, current or power. Power. This is power. Yes, power, port power. So significant of negative power we can see, but here you can see here, which was something like this before. So this portion we have reduced. This portion we have reduced, and the amount of back power flow or circulating power flow we can reduce using the introduction of delta. Now, what disadvantage that we are going to get here is, you can see here the peak value of power has reduced. That generally comes because the current itself reduces, length of the current phasor itself reduces. That is why the actual power flow, so we need to adjust in such a way that active power flow remains same, at the same time the circulating power becomes minimized. Same thing, this is the current, source current. Okay, so source current negative portion was something like this. Now because of this introduction of zero vector, zero phasor, actually why I'm saying like this, because of this portion, current becomes circulating through the switches, not to the, we have seen that initially source current was something like this. So source current means this current, it was having negative portion. Now you can see in PPS it is something like this. So there is a zero portion. How it becomes zero? Because now in this case here, previously this case it was generating this, this voltage was a square wave. Voltage was a square wave. But now this is in SPS. In PPS, the square wave is not a square wave, it's a quasi square wave. Okay, quasi square wave means you have zero voltage. Zero voltage is either these two switches are operating or these two switches are operating. When the upper two or lower two switches are operating, the current which is negative will circulate like this. The current will circulate. This current will not come here. This current will not be reflected back to this source, and that is why this current is shown zero. Okay, when zero is there, when voltage is zero, that means these two ports are shorted. These two terminals are shorted. Shorted means it is shorted through these two switches or these two switches. That means during this period, current is circulated in the bridge itself, and it is not going back to the source. And that is why whatever source has supplied, source is not bothering now. It is supplied and now it is circulated, and it is circulated and stored in the inductor. That is how PPS is helping improving the reduction in circulating power. Okay, one last topic I want to explain. Okay, as I told you that there is an inherent coupling between these three port powers. Okay, Now see, as I told you before, that whenever there is a power transfer between, so you have set phi 1 2 like this, so there is a power transfer between these two, whether it is positive negative, depending on that, power will transfer from port 1 to port 2 or port 2 to port 1. Similar for this, but there is a power transfer between these two. So if one port, this port power changes, this port power also will change, which is not acceptable. That is why we, in order to operate this in our desired manner, we need to operate this in decoupled control. Okay, decoupled control. Now, as I was telling you, this is just the extended version of DAB. D- D- So this is DAB, dual active bridge converter. Though it is just an extended version of DAB, in DAB we don't have any decoupling effect because only there is a power transfer between these two. When you introduce one extra edge bridge with one extra winding, there is a coupling between these two. Now we, if somebody thinks that we can extend this like 10 such bridges with 10 such winding, it becomes further difficult because there will be inherent power coupling between all the ports, which is currently it is happening. Here we having only three ports, so power coupling is there. If you have multiple ports, there will be multiple power coupling between, and controlling becomes very difficult. I have seen one paper where in cascaded edge bridge converter they have used a similar kind of thing with multiple secondary windings. They didn't talk about the coupling effect, but they have shown that the edge bridge converter is working fine. But in edge bridge converter there should not be a problem, because in edge bridge cascaded symmetrical cascaded edge bridge converter, all the power cells are having same power, so there it might not be a problem. But here, when you integrate different sources with the different ports, it will be definitely a coupling effect is going to make a difference. Okay, so how to, let's say if it is a TAV converter, how to operate this in decoupled control mode. Okay, it's very simple to think of, but becomes very difficult when you go deep into it. It's very simple, like this is the, these are the output variables. Okay, and these are the references, and this is the PI controller. Forget about these two parts. So output coming back, there is an error, and you compare with the PI controller. This is actually the system. This G matrix represents the okay. This G matrix, actually this G matrix represents the system. How to define G11, G12, G121, G22? This you can calculate. If you use any equivalent circuit, any of this equivalent circuit, you can calculate. We have used this equivalent circuit, and as I told you, the both the equivalent circuits are useful. If you, we have derived this G matrix using this equivalent circuit, delta equivalent circuit, and then you obtain the G matrix of the system. G matrix of the system. Now there is a coupling. There is a, so these are the inputs, that is phase differences. These are the inputs. It is generalized form. This is generalized form. These are the phase difference inputs, and these are the current or power. You can take anything, either current or power, because since output voltage is constant, so it is in current control mode. So whether you are taking current or power doesn't make any difference. This is the system matrix. Now our aim is to make, so so if you multiply, so this G11, if this is not there, this matrix is not there, then there will be, so if we say x0, so it will be G, it is function of both Z2 and Z3, that is function of this both Z2 and Z3. But our aim is to make it independent of these two. So how it can be done? What we do is we introduce an H matrix. This is the decoupled matrix. This is the decoupling matrix, which is inverse of H is decoupling matrix, and the inverse of G matrix should be G. No, this is wrong. It is inverse. H is decoupling matrix and inverse of G matrix. If you do this, then you will have only diagonal matrices, and then you will have the decoupling effect. Now the thing is, immediate question might come, that why not to have like this? Why not to have like this? Then we don't need this. We, let's say G12 and G21 is, if those two elements are not there, if we can minimize those two elements, then it is inherently decoupled system. But problem is, when you have these inductors, significant inductors, this inductance values are significant, then you cannot minimize or cannot reduce this diagonal element. Okay, one paper has suggested that put some capacitor here. You put some capacitor in order to nullify this inductance effect, and they have shown that this is how they can minimize the diagonal element, and they can achieve the decoupling control. Okay, what we did is, we used two methods. So as I was telling you, adjusting the leakage inductance values. Okay, we have done this one and partial derivative. These two methods we have used, and there are other methods are also there. These are also reported in the literature, but we have implemented this. So you can see here what I am talking about. Let's say these are the three powers: port 1 power, port 2 power, and port 3 power. You see here, at this point there is a change in power in port 2 power, but you see there is no effect on port 3 power. There is no effect. Okay, it is changing. The change is coming from port 1. If more power is required, that is supplied by port 1, and there is no change in port 3 power. Here power is reduced in port 3. There is minimal effect here, minimal effect in port 3, port 2, and the power is reduced. That means port 1 power is reduced. This is called decoupling effect. One power is changing, other port power is not changing. This is called decoupled power flow. So here also you can see here, average power is changing, but here minimal effect, 2.4 watt. Okay, here also power is changing, here it is affecting, but here it is only 5.8 watt. Okay, so this is how the decoupled power flow control can be achieved. Okay, with minimal effect on the other port power. So you independently can control the power of the port powers irrespective of power of the other port. Here how the phase difference phi 12 and phi 13 is automatically adjusting, and these are the currents I2, I3, and these are the reference. Okay, so you can see here one current is changing, other current is not affected. Current is changing, but this current is not affected, and similarly it is changing, but it is not affected. I've shown you this is using partial derivative, and this is Taylor series approximation. Okay, so here you can see that the currents, as I told you, if voltages of the ports are constant, then it doesn't matter whether you are showing power or current. So here also you can see that the currents are decoupled. There is no change in other port currents when one port current is changing. Okay, that is called decoupled power flow control. These are the waveforms. These are the TAB converter inductor current waveform. I have shown you DAB converter. This is a TAB converter inductor voltage waveform, inverter current. So port 1, port 2, and port 3. This is how inductor current looks like. Okay. ZVS is operation of ZVS analysis is little bit tricky. But only thing I want to tell you that it is dealing with the turn on and turn off time of the of the switches. Turn on and turn off. Generally what we do is we operate the switches. We cannot operate, we use MOSFETs. Now MOSFET generally we can use very easily up to 50 kilohertz, but if you want to operate it at 50 kilohertz, if you employ ZVS, its switching loss reduces significantly. How it can be done? It can be done by an energy exchange between the this leak. Uh, Forget about this leakage inductance. There is a parasitic capacitance there in the MOSFET equivalent circuit. Now, since we are using, why we are saying that inherent ZVS capability is there, because there is a leakage inductor. So when there is a leakage inductor and when there is a parasitic capacitor, there is an energy exchange you can do between these two elements, and you can ensure the path of current to flow during the ZVS operation. That is why this converter is capable of ZVS operation. So critical to achieve ZVS operation, because it becomes a little bit complex. In DAB, it becomes very easy, and in many places they have implemented successfully. Okay, even at 100 kilowatts also. So this capacitance I was talking about, this capacitance is so energy exchange between these two is very much important in case of ZVS operation. Okay. So since it is almost end of the session, so let me just tell you the applications. So autonomous DC microgrid application, as I shown you at the very beginning, and electric vehicle charging from renewable as well as from BESS, UPS, and also MV grid, LV grid are there, and you connect to the other grid or DC grid. Also, it's a very versatile. You can, with 3 ports, if you can control properly, you can integrate these three sources very easily. Okay, the advantages are, since it is okay, I thought of explaining why transformer we are using, why we cannot have DC-DC converter. Uh, Stepping up or stepping down, there is a limit for how much gain you can go with. Okay, we have always a limitation to that. So if you have this transformer based DC-DC converter, it provides isolation, and also this voltage matching capability is very much there. Okay, and isolation is there, bidirectional power flow. Okay, and overall stability of the grid, because there is a power exchange control you can do very easily. So that's why grid stability depends upon how, if it is a DC grid, then how firmly you can control the voltage of the grid. If it is AC grid, how firmly you can control the voltage and frequency, right? If it is active power, then active power flow. So frequency is related to active power, and reactive power is related to the voltage. Large number of switches and driver requirements, definitely it is there, and definitely there is a lower reliability. That's one point. So higher switching and conduction losses, these are all compared to DAB compared to DAB. And design is definitely complex because of this circulating power and decoupled control. So circulating current, this can be achieved. Circulating current can be reduced. Okay. Now what are the things that we have? It's a promising technology, definitely. So, but multiple since you have, it's a multi-port converter, so you can use it in the electric vehicle application as well. You can carry with the electric vehicle as well. As I told you that if you can increase the frequency, you can reduce the size of the converter at very high power level. The size of the converter will reduce further, and you can use in the onboard converter as well. Okay. So this supposed to be one of the best modulation technique, but though it is very complex, and two major characteristics that we need to talk about, need to address: back power flow and decoupling control. Okay, ZVS feature is also there. Okay, and ah, for high power application with high reliability. Okay, for high power application, I haven't seen these converters to be used. As I told you, I have seen DAB converters are used. Okay, for high power like cascaded converter application, but TAB converter I haven't seen now. Okay, so here is we are at the end of the session. Okay, thank you. So anyone is having any query? Transformer design is a little bit complex, but first thing that we need to talk about is the transformer kVA rating. So it depends on how much power you are transferring between the ports. Second thing is transformer leakage inductance is very, very important in this case. Okay, so it is generally what we found when we design the transformer, the leakage inductance is not suitable as we require. We have to add this. Practically we haven't implemented. We have bought one TAB transformer with a 3-winding transformer. We need to test it how much leakage inductance is, but what literature says that it is generally not matching. We have to add extra inductance. So design is important from the leakage inductance value point of view. That is very important. Core amorphous core. We have what we bought is amorphous core. Okay, that is what recently we bought. That is for 25 kilowatts.
If the participants have any questions, they can ask now.
Good evening, sir.
Hmm.
For bidirectional converters, how you are deciding the switching frequency?
Okay, see, switching frequency, you can have anything. Okay, now why I'm saying anything means switching frequency depends on your power level. Okay, if it is a multi-level converter, switching frequency is less. If it is low power converter, we can go up to 25 kilohertz or something like that. Now, in this particular converter, if you talk about DAB or TAB, there is a feature like ZVS. Okay, so you can go up to 50 kilohertz or 100 kilohertz. Now, question could be why it is 50 or 100? Why not more than that? Now, what I told that
No, sir.
either
On what
silicon.
basis? No, no,
I'm
on
telling
what
you.
basis you are going to select the frequency?
That is what I'm telling you. That if it is MOSFET device, then it is if you have ZVS on MOSFET device, generally at this power level, what we are using currently is MOSFET devices. Now, when it is a MOSFET device, there is a switching frequency limitation. So you can, let's say you are going up to 100 kilohertz, then what you have to do is using ZVS, its switching loss has to be reduced. Now, why we have to go to 100 kilohertz or 50 kilohertz or something like that? It depends on how much power loss you can accommodate and what should be the size of the heatsink. Is that fine? So size of the heatsink and why I'm saying how much power loss you can accommodate, as I told you, that heatsink size is crucial. Okay, you can go to, let's say, 70-80 kilohertz. You went till there, but you don't use ZVS, so power loss will be more. In order to accommodate that power loss, your heatsink size will increase. So if heatsink size will increase, your converter size will increase. So that is the, I generally say that even if from efficiency point of view, it is not that important. It is the size of the converter that makes more important. That is the most important. If you use gallium arsenide, this GaN devices, if you use, you can go further. It is limited by the power loss, size of the heatsink, and the device switching frequency limit. These are the things. You also can, if you go and see any device data sheet, it will not say this is a MOSFET you operate at 50 kilohertz or something like that. It will say about the time, turn on, turn off time. Based on that, you have to design the dead time also. So based on this, you have to limit the switching frequency.
Okay, sir. And one more question I have.
Sir,
Yes.
So how the impact of resonant frequency, how it affects the switching frequency?
What is that?
No,
Resonant
impact
frequency?
of resonant frequency on switching frequency. Is there any relation? Because when we are going for bidirectional converters, so what is the possibility we have when we are using the resonant converters in bidirectional
See, when it
power
is
converting and all?
when we have resonant converter, right? In resonant converter, it is not a particular frequency at which we operate. In resonant frequency, that resonant frequency, there is a range depending upon how much load you have connected. In order to have a suitable resonant region, the region, there is a, if it's, let's say, LCR or LLC or whatever it is, if you go for a resonant converter, it depends on load as well. So you cannot say this is the particular resonant frequency and you operate at that frequency. You cannot say directly like that. It depends on load as well.
Okay, I have two more questions, sir. One is
Hmm.
when you're going with bidirectional control, and you have already explained about decoupled control,
Hmm.
decoupling phenomena. So why can't we go with centralized controllers? And what are the drawbacks if we go for centralized?
Sensorless.
Centralized. Now you are
Centralized
using only two.
control.
Yeah, in decoupled, we are decoupling the system and using only two controllers, right? So why can't we go with four controller system?
4 controllers.
Yes, MIMO
4 con
controllers. Okay. And
No,
one
that's
more
fine.
thing is now interaction analysis between two channels, how they are going to affect. And you're anyhow when you're going with the decoupled system, indirectly you're converting the MIMO system into a CISO system.
correct, absolutely. Because
Yes.
this H
So
matrix is
interactions,
making that.
yeah, interactions. Anyhow, we are totally neglecting, but that is not the case with the original system. So when original system is considered, so interaction will be there between the loops, both the loops, maybe two loops if we or three loops, whatever you are considering.
Where it is
So
neglected.
in decoupled system, you are trying to minimize the coupling phenomenon, whatever it is.
Yes. We
Okay.
have introduced that H matrix in order to remove
Yes.
the diagonal elements.
Diagonal elements,
That is not
off
neglected.
diagonal elements, whatever.
Yes, off diagonal elements we are.
The
That is not
effect of one
neglected.
on the other is no effect of one on the other is reduced. Maybe you can.
Yes. Read. That is the aim. That is the requirement.
Yeah. But it is reduced, but not totally eliminated. Maybe the case. So we have three
Okay.
controller system. So that is
Okay.
what I'm asking. If that is the case, what could be done?
Elimination means till you want zero effect.
No,
Because
sir. The
the
second effect.
results I have shown you, there it is when there is a change in power is 200 watt, there is change in I think 2 to 3 watt other port power.
Yes.
That is sufficient. You want more on this.
Yeah. Yes. If
Okay.
it is to
So,
be more, what
so
needs to be done?
okay. No, we haven't tried on that, but what we did is we use this thing, this H matrix, because this thing is till now it is reported, we have seen that H matrix, based on H matrix we can nullify this off diagonal matrix and we can achieve decoupling control. But what you are saying is 4 controllers, one definitely disadvantage will be the tuning the 4 controllers will be much more complex than getting the H matrix, which is directly inverse of the G matrix. G matrix you can calculate
Yes.
from the delta equivalent circuit.
Yes. So Z matrix inversion will again create a problem. So I'm asking that, had you concentrated any problems like that? Just for information sake, I was asking, nothing more than.
Implementation means we have worked on this in simulation work. Okay, hardware we have not started yet. We will definitely in project will work on this and we'll see how beneficial it is and how effective it is.
Okay, the parametric uncertainties also has to be considered. Maybe that
Yes,
also
definitely.
has not been considered, I think,
Correct.
in that
You are
simulation
correct.
case study. What? Yeah.
That need
Okay,
to be
sir. Thank you.
yes. Okay.
Yeah. Thank you, sir. Thank you.
Sir, I have a question. Sir, even though you have mentioned that one, so why a transformer? Because without using DC to DC converter directly, we'll be using one rectifier, but we'll be using one coordinated controller so that we can give power to the different applications, varying the internal phase shift. So the using of transformer increases the complexity. So can it happen that directly controlling the rectifier, you can have different power for different applications?
Actually, I cannot hear your question properly.
No, sir, you have mentioned the question that thing that why are you using transformer, why not DC to DC converter and their individual control? So instead of that, using directly one rectifier, and by using that coordinated controller for that particular rectifier, you can have the different phase angles for different applications.
Okay, you are saying we use a rectifier. After that, what we use? A DC-DC converter.
No, DC to DC converter will not be there. That rectifier itself will be controlling so that we can charge the EVs and we can give power to the
Okay.
DC microgrid
So
as well.
rectifier, from where will you charge? From where will you take the power input to the rectifier?
No, no, input will be the normal AC supply. That will
Then
be
how
rectified, but that
isolation will be? Isolation?
okay, isolation
Isolation,
only it will be a
isolation
problem.
is required. Now for
Okay,
isolation, what you can say is between grid and the rectifier, we can put a transformer. But that transformer
okay,
will be a 50 hertz transformer.
okay,
Okay, that transformer we want to eliminate, and or that transformer we want to reduce the size of that transformer. Now in older days, we used to had this 5 volt power supply, 5 DC 5 volt power supply, which were very
okay,
heavier, right? So it
okay,
was
okay.
having this 50 hertz transformer. Now we have
Yes, yes.
SMPS power supplies. Those are
Mhm,
this
yes.
high frequency transformer, which is a very lighter and also size is very small.
Okay. Okay, thanks. Sir. Sir, another question is there. Sir, what are the practical challenges of connecting different sources like fuel cell, solar, PV? Because you know that when you are connecting two, three alternators in parallel, you have to consider some parameters so that there will be no circulating current. Is there any practical challenges so that you have to that one we have to consider before connecting these sources in parallel, like to form one grid?
See, one thing I can tell you, not PV, not fuel cell or anything. Just one thing you remember always: if you have multiple sources, one has to control the voltage, other has to be in current control mode. Then you
Okay.
definitely control the circulating power. Let's say
Okay.
you have
Okay.
three sources. One source,
Yes,
let
sir.
it control the voltage, and other.
Yes, sir.
It generally, this is the general practice. This is state of art. When you
Yes,
have
sir.
see an inverter, a solar inverter, it can be act as a standalone inverter or can be grid connected. When it is in
Yes, sir.
standalone mode, it is voltage and frequency control mode. But when it is
Yes, sir.
connected to the grid, it is in current control mode. So
Okay.
similarly, if you have, let's say, three sources, let one
Okay.
source control the voltage and other sources you put as other sources you put in current control mode. There are other possibilities are also there. If you go through literature, this master slave and other things with communication and other things are there. But in general practice, if you pen on paper, if you have two DC sources, if you connect, if there is a voltage mismatch, definitely there will be a circulating current.
Okay, sir. Thank you, sir.
Hmm.
Okay, sorry for the interruption. Actually, because of time constraint, we have to stop the question answer session here. And if any of the participants have any questions, they can directly mail to the sir. So we would
Yeah?
like to extend our deep sense of gratitude to
But
Professor
PV
Indrajit
control, which
Sarkar
type of
sir
control is
for his
here?
detailed lecture on the control of triple active bridge converter, different phase shift techniques, and its application
We
in
have
DC
not
microgrid.
explored the
We
nonlinear
truly
control.
appreciate you and
You
your
can write.
valuable time for
We
this
have not.
short-term course STEM
We
2023.
have not explored.
Now, thank you so much, sir.
And thank you.
We'll start the valedictory ceremony after 10 minutes. We would like to invite you all to attend the ceremony. It's so wonderful to see you all here. Thank you everyone. A very warm good evening to one and all. I would like to invite our dignitaries with a request to come on the dais and occupy the seats. Thank you, sir, and thank you, ma'am. It's with tremendous pleasure that I am Anindya Bharati, a research scholar at NIT Rourkela. Welcome you all to this valedictory program of hybrid mode short-term course and faculty development program on sustainable technology and energy management of hybrid microgrid STEM 2023, which is successfully organized by the Department of Electrical Engineering, National Institute of Technology, Rourkela. Now I would like to invite the coordinator, Professor Prabhat Kumar Rai sir, to address the guest and participant with his words.
Good afternoon, one and all. Esteemed coordinators, STEM 2023, Professor Mona Lisa Patnaik and Professor Arnav Ghosh, my faculty colleague, Professor Indrajit Sarkar, my dear participants from different institutes and organizations, ladies and gentlemen. Yes, now you are in the end session of our 5-day long short-term program. So far as overall organization of this program is concerned, in total 232 participants have attended this program. Participants are mainly faculty members and few research scholars from different institutes and practicing engineers from different industries. Expert members, those who have delivered their lecture during this 5 days program, are mainly from institutions of national importance such as IITs, NITs, IIIT, and one professor from Sri Lanka, Sri Lankan University, who is our project collaborator in one of our Indo-Sri Lanka DST project. So in these 5 days of deliberations, basically we have focused on issues and challenges of microgrid implementation and power management. In particular, we have discussed starting from maximum power point tracking, design and control of converters, then grid integration issues and challenges of photovoltaic system, wind energy system, then adaptive control of microgrid, protection of hybrid AC-DC microgrid, power management in DC microgrid, and finally sizing of energy storage devices in electric vehicles. So in order to provide practical idea to our participants, we have conducted one case study, or we have discussed one case study, that is microgrid, which is implemented in one of the buildings in Sri Lankan University. And so far as laboratory sessions are concerned, we have given emphasis on design of wind turbine emulator, MPPT implementation in wind energy system, and power management in hybrid AC-DC microgrid. So in total, we have conducted 12 theory sessions and 3 practical sessions. So we are very much happy to share our updated research in this forum to different institutes and organizations through our participants. Many sessions were very much interactive and fruitful discussions were made among experts and participants. So by our own technology, own knowledge, if we're able to find out the solution to our problem, then we can achieve Make in India, Digital India, and finally Atmanirbhar Bharat mission of our government. So I must thank my fellow coordinators, Professor Mona Lisa Patnaik and Professor Arnav Ghosh, for constant support and tireless effort in organizing this course. My sincere appreciation and thanks goes to our research scholar volunteers for such nice arrangement of this program. At last but not the least, from my core of my heart, I extend my thanks to all the participants for attending this program. Thank you all.
Thank you so much, sir, for your precious words. Now I request Professor Prabhat Kumar Rai, sir, to present the certificate to our participant. First, I would like to invite our student presenter to come on the dais and receive the certificate of appreciations. Mr. Pradimna Kumar Behera. Mr. Mendi Balaji. Miss Anindya Bharati. Now I request the participant to come on the dais and receive their certificates. Uh, P. Abdul Ishak. B. Venkat Narayan. Pradyumna Kumar Behera. Shobhit Nankialar. Chinmay Jagdev Jena. Mendi Balaji. Ramesh Chandra Khomari. Bhanu Pratap Behera. Thank you, sir, for presenting the certificates to our participant. Now I request Professor Monalisa Patnaik ma'am to present the certificate to our participant. Vibhudatta Misra. Suchismita Patel. Anindya Bharati. Manas Ranjan Jena. Tejaswini Shahu. Rasmiranjan Swain. Jaydev Meher. Kaburu Srinivas Rao. Kartrubikas Burma. Golden Kumar. Subham Sinha. Harsh Gupta. Hassan Raja. Subham Kumar Maji. Rakesh Kumar. Pragyansri Ray. Thank you, ma'am, for presenting the certificates to our participants. For online participant, we will send their certificates and related materials as soon as possible. Now we would like to listen some feedbacks from our participant. So I request the participant to give their valuable feedback and experience regarding this short-term course STEM 2023. Now I encourage our online participants to please kindly give your feedbacks for this course. While giving feedbacks, please kindly turn on your camera.
Good afternoon, dear participant. Please share your valuable feedback. So in near future, when we are going to conduct, so we can rectify ourselves as well as we can also design the course as per your requirement. Please share your feedback.
Now I request our offline participant to please come on the dais and give their
Dear
valuable.
organizers and esteemed faculty members, I am Satyanarayana from Srinidhi Institute of Technology, Hyderabad. I am truly grateful for the part of this FDP. I learned many things and in my research area and different areas of the microgrid. I'm immensely grateful to the faculty members, those who are saved their dedicated time and their expertise, they deliver the informative lectures with real-time examples. Finally, I would like to express my heartfelt thanks to their organization team, which are the conducted the FDP with um, meticulous planning and seamless coordination. To this, finally, I would like to say this program is enhances our knowledge in different areas of the microgrid. And I would like to say whether this is the platform correct or not. My suggestion or whatever may be the anyhow, so many expertises are there. What are my thoughts I'm sharing? So these days, the importance of the electrical engineers, electrical sections are gradually decreasing. So many faculty members and students are moreover they are encouraging or interested to joining the CSC related branches and AI, artificial intelligence, and machine learning, etc. So organizers and institute engineering colleges are moreover they are decreasing the number of sections in electrical departments, and we don't know whether the future whether it is increasing the importance of the electrical engineering. So my sincere request is we have this so much of expertises in electrical engineering, whether they include the new courses which is collaborating with the electrical like AI, robotics or whatever may be the machine learning, incorporate the electrical um with a subject to encourage the faculty members as well as the students to join this course. That is my thing. Thank you, one and all.
Thank you so much, sir, for sharing your experience, and we will try our best to implement whatever you suggested here. Thank you, sir.
Thank you, ma'am.
Yeah. Good evening to one and all. Myself, Dr. OVSR Varaprasad from Gayatri Vidya Parishad College of Engineering Autonomous, Visakhapatnam. So first of all, I would like to thank the organizers for selecting me to attend for this particular workshop. Professor Parvat Kumar Ray sir, Monalishka Patnaik ma'am, and Arnab Ghosh sir. So the entire sessions went very well. Especially, I would like to quote some of them. That wind energy conversion system emulator, and today's the last lecture corresponding to that TAB converters. So with in line to the microgrid applications and as per the program is concerned. So it went very well, and the deliberations are very much informative. And I would like to take some kind of knowledge with this particular workshop or short-term program, especially in the morning session by Professor Ghosh sir. He mentioned that the relation between the teacher and the student must be like a sun and sunflower. So until the students is existing, there will be a continuous learning is necessary as per the national educational policy for the teacher to the cutting edge technologies for the upgradation of skills and knowledge to disseminate to the students. So it is very much informative, and thank you very much for the organizers for your timing and concern. I know how difficult it is to handle the workshop in both online and offline mode, but in view of all these aspects, I would like to say that it is well organized, and thank you very much for this kind of workshop. And we will expect this kind of workshop in sooner also. And thank you very much for giving this opportunity to share my feedback. Thank you.
Thank you so much, sir, for sharing your thoughts with us.
Sir, can I go next?
Yes.
Yeah, hi friends. Good evening. It was really a great session on all the workshops we had in STEM 23. Heartfelt congratulations to every brother and sister who made this successful show. I thoroughly enjoyed every session. Looking forward for the workshop materials. From my whole heart, and every piece of session went well. This is much of need for people who are in the industry, who cannot actually prioritize their timelines to work, to learn everything. So this is a very wonderful initiative from NIT Rourkela. I'm looking forward for a couple of other FDP programs in this space. Thanks a lot, Professor Arnab. Thanks everyone. Namaste.
Thank you so much, sir, for your valuable feedback.
Thank you.
Now I request our offline participant to please kindly share your feedback for this autumn course.
Good evening, one and all. First of all, I say thanks to Dr. P.K. sir, Dr. Monalisa Pattaik madam, and Dr. Arnav Ghosh sir for initiating and conducting this FDP program. We actually enjoyed this program and you learning something. Actually, I joined 8 months back to research in PhD. This is very helpful to us. I am expecting more FDs from this NIT Rourkela in future. For that, you definitely participate, definitely in online or offline versa. Your cooperation means your here research scholars and faculty cooperation is very good. Okay. Say finally, I would like to express thanks to who are directly or indirectly success this program. Okay, thank you.
Thank you so much for your valuable feedback. Any other offline participant, if you want to share your feedback, then please come to the stage. Okay, thank you everyone. To propose the vote of thanks to all the dignitaries and participants, let me invite the coordinator, Professor Arnab Ghosh, sir.
Thank you. And very good afternoon, all the esteemed professor as well as the dignitaries and the esteemed participants from different institute as well as some industries. Those are attending the course and make the course more successful. As per my view that we are getting huge participations. I hope we are trying to mitigate or your level of expectation. Still, I hope in near future, if we are going to conduct any course, I hope your active participations from our maybe course or conferences from your end. Okay, so thank you for sharing your valuable comments with us, as well as I'm requesting all of you kindly fill the feedback form that we have already shared, as well as madam also shared some information form related to certificate preparations. Kindly fill both of them, as well as we are going to share all the sessions, okay, recorded sessions, and for your better for your future references. So in our WhatsApp group we will share it again, okay, as well as we are going to share all the materials that whatever the expert will share with us, as well as the recorded version that I have already told you. And that's it. As well as I want to thanks all the active participations by our research scholars and that other PG students who are giving continuous effort to make it successful. Without their help, this is not possible. As well as our my Professor Prabhat Kumar Ray sir, Professor Mona Lisa madam, I am also thanking both of them for always supporting me to encourage to conduct this kind of course. In near future, again, we are planning to conduct in different kind of course as well as conferences. That's it from my end. Thank you. Thank you all of you.
Thank you so much, sir. Now I hope all of you are benefited with this hybrid short-term course and faculty development program. As your team has made an effort to make you keep you comfortable and entertained throughout the course. Thank you everyone for your presence over here. Now I would like to invite you all for to join us for refreshment. Thank you. Thank you everyone.
Thank you.
Thank you so much. Bye bye.